Hello. Today, we are going to take a look at a very interesting topic, the hidden battle happening every time you press a button in a skyscraper. This is the elevator speed paradox. We're about to dive into a 2,000-year fight between the raw power of engineering and the delicate reality of human biology. It's a story of how we built cities into the clouds, and why, despite having the tech to go faster, we are currently stuck in a biological bottleneck. Think about your morning commute. Not the train or the car, but the invisible commute, the vertical one. Modern engines are marvels of power. They can easily push an elevator cabin past 20 meters per second. But there's a catch. Even if the machine is ready to fly, the human body acts as the ultimate speed limit. This paradox is why your trip to the 50th floor hasn't actually gotten much faster in decades, even as our buildings have doubled in height. To understand where we are, we have to look at where we started. The origins of vertical transport go back over 2 millennia, to Archimedes in 236 BC. There were no motors here, just a rudimentary system of pulleys and wooden platforms powered by brute force and animal muscle. It was simple, yes, but it laid the fundamental blueprint for every skyline you see today. By the 18th century, elevators weren't for construction, they were for the elite. This was the era of the royal secret. King Louis XV had a private flying chair installed at the Palace of Versailles. Its job? To whisk him from his apartment directly to the quarters of his mistress, bypassing the prying eyes of the court. The elevator had officially transitioned from a primitive tool to a luxury item, hidden behind palace walls. But there was a dark side to this luxury, a single point of failure that turned these machines into vertical guillotines: the rope. Before the mid-19th century, elevators were essentially death traps. If that single hemp cable snapped, there was nothing but a terminal plummet to the bottom. In this era of engineering, gravity always won, and that fear kept the world on the ground floor. Everything changed in 1853, thanks to Elisha Otis. He didn't just build a better elevator, he tamed gravity by inventing the safety brake. The technical logic was brilliant. He used a heavy steel wagon spring that, if the rope snapped, would instantly mesh with a notched ratchet. Think of it as the machine biting into the guide rails to save its passengers. To prove his invention to a skeptical public, Otis staged a legendary stunt at the 1854 New York World's Fair. He stood on a platform high above the crowd and ordered a man to cut the only supporting rope with an axe. The rope snapped. The crowd gasped. But the platform stayed still. Otis calmly looked down and proclaimed, "All safe, gentlemen, all safe." In that moment, the modern skyscraper was born. So, why don't we have 100-mile-per-hour elevators yet? We certainly have the motors for it. We can build engines capable of 200 kilometers per hour. But we've run into a wall that no motor can climb. While engineering allows for almost unlimited velocity, the passenger inside has become the limiting factor. We have the muscle, but our bodies can't handle the hustle. Biology is now the ultimate bottleneck in vertical transportation. Our inner ears and internal organs simply weren't evolved to handle the rapid pressure shifts and vertical g-forces that a high-speed elevator can generate. Even if the machine is capable of more, the human frame is at its breaking point. Let's look at the science. As you go up, atmospheric pressure drops, specifically at a rate of about 0.12 millibars per meter. This causes the air trapped in your middle ear to expand and push against your eardrum. That's the ear pop. Luckily, your eustachian tube acts like a one-way vent, letting that air escape outward relatively easily. It's annoying, but rarely painful. But the trip down? That is a different struggle entirely. As you descend, atmospheric pressure rises rapidly, creating a vacuum that clamps the eustachian tube shut. Because that tube is essentially a one-way flutter valve, it resists letting air back in. Going down hurts more because your body has to work significantly harder to force that valve open and equalize the pressure. Then there's the Luna Park effect. Your vestibular system, the balance center in your inner ear, is incredibly sensitive. If vertical acceleration exceeds just 1.5 meters per second squared, the inner ear rebels. You get nausea, spatial confusion, and dizziness. This is why engineers have to strictly cap how fast an elevator speeds up or slows down, regardless of motor power. To beat these limits, ultra-fast towers like Taipei 101, which hits 16.8 meters per second, or the Shanghai Tower at a staggering 20.5 meters per second, have to treat their cabins like airplanes. They use aerodynamic shrouds to slice through the air and active pressure seals to keep your eardrums from rupturing. It's literally aerospace engineering inside a concrete shaft. But the future of the elevator isn't just about raw speed anymore. It's about math over muscle. Instead of trying to fight biology with faster motors, we've smartered the traffic. Modern destination control systems use algorithms to group people by floor before they even step inside. By reducing stops and starts, we've made the commute faster and more efficient without ever needing to increase the actual velocity of the car. The bottleneck has shifted from the engine to the algorithm. The story of the elevator proves that true innovation isn't just about defying gravity. It's about accommodating humanity. We've mastered the machine. Now, we're mastering the experience of the people inside it. So, next time you step into that little metal box, remember, without a few stubborn inventors and one very dramatic safety demonstration, we might all still be climbing 40 flights of stairs. Civilization owes elevators more than it admits. If you want to see more content like this, don't forget to subscribe and hit the bell so you never miss the next deep dive into the technology that builds our world.